Okay, I'd like to make a few additional remarks on Lenz's law. So first, let's review what Lenz's law is. It's a shortcut for remembering which way an induced EMF is oriented due to electromagnetic induction. Okay, so we're talking about Faraday's law here. Lenz's law just gives us the direction. Faraday's law gives us the magnitude. And actually Faraday's law gives us the direction too. But this is a shortcut for remembering the direction. And here's what the shortcut is. So nature will create an induced EMF that produces a current, which in turn produces a magnetic field. Okay, so that's Faraday's law, is that it creates an EMF. And that EMF will produce a current, which produces a magnetic field. And the magnetic field that is induced will oppose the change in flux. That's the d phi dt term. Okay, so the B field that's induced will oppose the change in flux. So how it works in practice then is we use Lenz's law first to decide the direction of B induced, okay? Because B induced is going to oppose the change in flux. So we use Lenz's law to find the direction of B induced, and then use right-hand rule number 3 to find the direction of the current, and that creates that magnetic field. So if we decide that the induced magnetic field is out of the page, then I would put my right hand, using my right hand, I would put my thumb pointing out of the page, and my fingers tell me which way the current goes. If it's end of the page, if it's to the left, to the right, and so on. So whichever way the induced magnetic field points, which is what we decide that direction using Lenz's law. Whichever way it points, I use my thumb in that direction, and my right hand, rule number 3, my fingers curl in the direction of the current. Okay, so let's go through some examples. And in all these examples, let's suppose that the flux simplifies to just B times A, the magnetic field times the area. All right, so example number 1, say I have a constant magnetic field that's coming out of the page, going through an area that is shrinking. Okay, so what's happening to the flux? Well, the flux is B times A. B is constant, A is shrinking, so the flux is shrinking. And so what does Lenz's law tell us? Lenz's law tells us that nature will induce a B field, B induced, to oppose this change in the flux. So if the flux is decreasing, then B induced is going to be trying to increase the flux. And if we want to increase the flux in this situation, then we would expect B induced to be out of the page. Okay, so that it adds to the existing B that's already there. Okay, so if B induced is out of the page, it will add to this B that is already here, and that should increase the flux in an attempt to stop the flux from shrinking. Okay, so we know this from Lenz's law. And then we use the right-hand rule to find the direction of the current, so that we know that the induced current, in this case, is going to be counterclockwise. All right, let's look at another example. This time, the magnetic field is constant and out of the page, as before, but now the area of this loop is increasing. So the rectangle is growing. And by the way, just to be extra clear about the difference between these two magnetic fields, this is the induced one. I'm going to call this one the external magnetic field. This is the one that's already there. It's created by some external agent. Okay, so we're distinguishing that and the induced magnetic field. All right, so what's happening to the flux in this case? Well, B is staying the same, but A is increasing. So that means that the flux is increasing. So B induced will be in what direction? Well, Lenz's law tells us that it's going to oppose this change in the flux. If the flux is increasing, then the induced magnetic field will be into the page, because that will subtract from the strength of this field. So while the flux is increasing, this will try to decrease the flux, or equivalently keep it from increasing so much. Okay, so this is Lenz's law. Tells us that the induced magnetic field must be into the page in this case. And so now right-hand rule, the induced current is clockwise. Okay, the next two examples, the same as the previous ones, but now I have flipped the external magnetic field. Now it's into the page in both cases. And in example 3, the area is shrinking, and in example 4, the area is increasing. So this would be a really good time for you to get some practice. So pause the video here and try to do these two yourself. See if you can figure out what the direction of the induced current is in these two cases. Use Lenz's law and the right-hand rule. So pause the video and give that a try. Okay, so let me go through them. In this case, the flux is shrinking because the area is shrinking, which means the induced magnetic field is going to try to boost the external magnetic field so that this flux doesn't shrink so much. Okay, so B induced is going to be into the page. And therefore, the induced current is going to be clockwise. Okay, in this case, the flux is increasing. So nature is going to try to resist that by creating a magnetic field that opposes this increase. Okay, so it's going to create a magnetic field that's out of the page, because that will subtract from this external field that's into the page, right? They're in opposite directions. So there's a partial cancellation here, and that's going to counter this increase in the flux by decreasing it a little bit. All right, and then the induced current is counterclockwise. Okay, so we've done 4 examples where the area is changing, but the magnetic field, the external magnetic field, is not. Another way to change the flux, though, is to change the external magnetic field. So let's do examples where the area is constant, but the external magnetic field is increasing. So first, let's say the magnetic field is out of the page and increasing. So that means the flux is increasing. So that means the induced magnetic field will oppose the external one. And so that means that the induced current is going to be clockwise. Okay, down here. Here, the external magnetic field is decreasing. So the flux is decreasing, which means the induced magnetic field is going to try to boost the flux. So it's going to add to the existing magnetic field. So it's going to be in the same direction as the external magnetic field. And the current that's induced from this is going to be counterclockwise. Okay, last 2 examples. The same as the previous 2, but now the external magnetic field is into the page. So first, let's say that it's into the page and increasing. Then that means that the flux is increasing, which means that the induced field is going to oppose the external field in an effort to keep the flux from increasing. And so the induced current is going to be counterclockwise. In this case, B is into the page and decreasing. So that means the flux is decreasing. So the induced magnetic field is going to try to stop this decrease. So it's going to try to boost the external magnetic field, so it'll be in the same direction. And then the induced current then is clockwise. So I went through all 8 permutations here. The next thing to consider is, well, there's a couple more things that we could consider. One thing that could change the flux also is the change in the angle between the loop and the external field. So I assume that the external field and the loop were always perpendicular to each other in all these cases, just to simplify things. But if you change the orientation of the loop or the orientation of the external magnetic field, that will cause a change in flux too. The other thing that we haven't considered here is, although we looked at B changing
and A staying fixed and B staying fixed and A changing. We didn't address the case of what if both B and A are changing, okay? And that is the problem that we did in handout 23, and that will be the topic of my next video.